Now I wanted to talk to you about how to identify forces in a word problem or in a problem with a picture. So, you might not be told there is a normal force in the y direction, there is a spring pulling in the plus x direction. You might just be given a picture of a situation and asked to solve it, which, the next step from the beginning is going to be like drawing a free body diagram. So how do you get from a picture to a free body diagram so that you can apply these rules that we've learned? So we have a recipe for doing this. This is from a textbook, Physics for Scientists and Engineers by Knight. This is not in our textbook. So for those of you not watching the videos, apologies, this is a very useful thing to do. So here is how we identify forces on an object. So this is in, presumably in a word problem or something like that. Okay, so the first step is to identify our system, and that is distinguish what we're considering our system and what we're considering our environment. I guess I should say maybe our system, versus the things that are in the environment. So let's do a little example as we go, I guess. So let's say we have a problem with a skier skiing downhill, and maybe we're given a picture that looks like this. We have a skier. That's not great. Anyway, something like that. So they're going down a hill, and maybe we're asked to find the acceleration of the skier or something like that. So identifying the system versus the environment. Well, in this case, the system that we're going to be interested in, the thing that we're going to want to find the forces on, is the skier, right? So the skier is our system. The environment is the slope and the trees and the birds and etc. So step 2 is to draw a picture if you have not already. And this needs to include all, things like ropes, springs, anything else that might be exerting a force on the object. As always, the picture doesn't have to be good. Instead of a skier, I could draw a square, and the picture will work just as well. Step 3 is kind of the clever part. This is to draw a circle. It doesn't mean like a perfect radius circle, really. It means like a loop around your system and your system only. So try to not get any of the environment in your circle. So for this case, maybe I would draw something that looks like this. So I've included my skier. I have tried not to include the ground. Step 4 is to locate every point where something touches the system. So in this case, there's only one place things touch the system, and that is at the bottom right there. If the skier had a rope, they were like pulling a rope behind them or something, then we'd say, oh, well, this rope is also touching our system over there, and so we need to include that. But for now, as it was, it's just this point down here. Step 5 is to identify the forces that we have at each of those points of contact. And in general, there will be a force every time something is going through the circle. There probably are exceptions, but 90 whatever percent of the time, there is going to be at least one force at each of these. And we want to identify that in terms of, not just, oh, this is a force, but like in terms of its name or variable. So we want to name the force that we have at each point. So here we have our skier touching a surface. At a surface, we have normal forces. So I'm going to put right here, I'm going to put, oh, there is a normal force at that point. And I will remember that there's a normal force. It also is possible, depending on what's going on in the problem, we may also have friction at that point. So maybe I need to put both of these. And if the skier is, if the skier is moving down the hill, that would be kinetic friction if they were perched, pointed downhill but not going, it would be static friction. So we have named both of the forces, and these are at the same point. These are both where the skier is touching the surface. That's okay, we can have more than one force at a point, especially at surfaces. Okay, step 6 is to identify any long-range forces. So remember, we can separate our forces into contact forces and long-range forces. So contact forces are anything that touches your object and exerts a force on it. So that is surfaces, ropes, springs. And we only have one long-range force in Physics 106, that is gravity. If you are going to use this trick in later classes, like Physics 107, there are other long-range forces you will have to worry about, but in this class, the only one we will have will be gravity. In this case, do we have gravity on the skier? Yes, we do, so maybe we'll write Fg floating off in space to remind us that there is gravity also. And then, from this information, from what we have done, we can be confident that we have found all the forces, and step 7 is to draw a free body diagram. So then with that, we can do things like find the components of the forces and combine them to find net forces, and so on. So here, for the skier, I draw my object as a point. I draw all the forces as vectors from this point. So gravity is going to be straight down. Our normal force is perpendicular away from the surface. And let's say the skier was going down the hill. So it's kinetic friction, and the kinetic friction is going to oppose that downhill motion. So it's going to be pointing up. And now this is a complete free body diagram. I might want to add other things. If I knew the angle of this slope, I could add that onto my diagram to say how big these angles are. And then I can start figuring out how big components are with trigonometry. All right, so let's do one other example just as practice. Let's say I have a car being towed uphill. And let's say the hill has friction. Okay, so our picture is going to, we'll follow the steps for real. So the first step is to ID the system. Well, let's find the forces on the car. That's the only thing in the problem. So draw a picture. So we have a car being pulled by a rope up the hill. And now we could draw a circle around the system. So it is like that. We want to identify every point where something touches the system. So that is, we have contact at the wheels, and we have contact here where the rope is. And at each contact point, we need to identify the forces. So here we have tension, the tension of the rope. Here we again have normal force and also friction. If it is being towed uphill, if it is going uphill, it is moving, so that is kinetic friction. And our long-range force, we have gravity also, pulling down on it. And now we're ready to make a free body diagram. So we have gravity down, gravity straight down, I should say. We have our normal force perpendicular away from the surface. We have our tension. I guess I should label this. We have our tension. Remember, ropes can only pull in the direction they're pointing, so our tension is going up the hill. And if we're going uphill, our friction is opposing that, so our kinetic friction is down the hill. There's a couple other things we could add to this. Remember, our normal force is always perpendicular to our surface. Our kinetic friction is always parallel to our surface, so we know that this has to be a right angle. Assuming that our rope is parallel to the ground, right, if these two are lined up, which you would be told they are, or if you're not, you can assume they are if that makes sense with the picture. This would also be a right angle, and you can use those to figure out other angles that might be useful in that problem. All right, so we'll be doing more of this sort of thing for sure, but hopefully this gives you a good idea of how we can go from word problems or pictures to a free body diagram that we are then ready to use Newton's laws on.